Hi and welcome back to a new episode. Today's episode is about random walk. What is a random walk? How can we use R to determine if we are working with time series data that behaves like a random walk? What is the purpose of using random walk? What is a mathematical equation for a random walk? And we will explore different packages to understand that we're dealing or not with random walks. Let's see next time series and random walk in R. Now, among the different applications of random walk, we can find the application in physics for modeling the Brownian motion, the molecules' movement in liquids, for example. In ecology, it's used for understanding how the ship moves. In informatics, it could be used for estimating the website that we're working around the world. Let's see more about random walk. But first, we have to discuss what is random walk by using a mathematical equation. I'm going to show you two different types of random walks, and we'll discuss the mathematical equation. You can see here I have something called random walk and random walk with drift. A pure random walk is going to be when we have no constant value here. So you can see why I say a constant value, right? Of course, because we have a time series data. You can see we are going to call it x in this case. X determined in each step, we call it t for time. And we can see here each step at time t is going to be determined by the previous step or previous value plus a random noise or errors that are distributed as we usually determine white noise, as we discussed in a previous video. We can use normal distribution with mean 0 and variance sigma squared. Remember that the properties of white noise is equal variance and stationarity. Then, if you can see, a random walk is going to be a time series where our current value is going to be explained by a previous value plus some error. That's what I is trying to say. And then a random walk with drift is going to be that each step we add a constant value. In this case, we call it alpha. That means that every step we will add another value, alpha. Why I say another? Because in the past value, we also added. As you can see here, for each step t, we are adding more and more and more values alpha. That means we will have been adding alpha t times. And that's the reason we call a random walk with drift and alpha as deterministic trend. Why? Because every step is going to be add or additionate with alpha. And we will be increasing our time series or decreasing depending on the value of alpha. And some important details about random walks is that you can see here, the first part here I have is gonna be x t minus 1. So I'm just rewriting. If this is the mathematical equation for a time t, then this part here is gonna be the mathematical equation for x t minus 1. So I just replace it, and as you can see, every time I want to rewrite my x t minus I minus 1, minus 2, minus 2, you can see I can rewrite it with a previous step or previous values. And then at the end, in my pure random walk, I will have a sum of different errors plus the initial value x sub 0. And not that x sub 0 doesn't have to be 0. Sometimes we will work with x sub 0, the initial value, as 0 for better understanding, for simplicity. However, it doesn't have to be the case. And as you can see, the expected value of our time series data in a t time is going to be our expected value. Why? Because if we try to find the expected value for the sum, it's going to be the sum of the different expected values of the errors. and the expected value for our errors is 0. So at the end, we're going to be adding zeros multiple times, and then it's going to be only the expected value of x sub 0. The same applies for a random walk with drift. However, here we will see that each time I'm rewriting my x t minus I for a moment I, of course, in the past, you can see I'm adding alpha another time, and then I will have alpha one time plus another time, two times. But if I rewrite it again and again, I will have 3 times alpha and so on. Then we will have t times alpha. And that's the reason that as for our pure random walk, our expected value for a random walk with drift, we will have expected value for our time series as the initial value plus t times alpha. And let's see, let's create a first example using R. I'm going to use the library dplyr for using a certain function we will discuss. You can see here, I'm going to create a vector with 100 values. In this case, all of them are going to be 2. However, we'll replace them. It's just for creating a vector. Let's see. Remember that we're going to be working with white noise, and then we have to simulate some white noise. It's important to notice too that our white noise is random. So the response for our random walk are going to have some randomness components or components with randomness. Then I add R, and it's important to understand that we're working with some time series, so we're going to use X as our date. In this case, I'm going to work with days, as you can see, and adding 100 days for the initial day while we're working. In this case, January 1st, 2021. Okay, and here is how we're going to create our random walk. You can see here, I'm going to go along all my values in Y. That's going to be our time series values. You can see I'm rewriting each step on time. We call it I in this case, but this is going to be something like x of t. But in this case, this is going to be something like this. Of course, I'm just using y instead of x. It's the same. And as you can see here, my previous value will be added to our random noise in that moment I, moment t, to our current value. And then we can see something like this. One step behind plus the random noise for the present is going to be our current value for our time series. And then we're going to rerun this. You can see here y, first, of course, 100 values 2, and then we rerun all this, and we will see how it's going to be modified. So here, there you go. We have created our first random walk. Very important why I use dplyr. Well, because there is also some function called lag that's going to be, we're going to move back each position for y to retrieve the previous value or the previous day in this case. I'm going to call it y2 to show you how this works. You will see, and we will use it. We will see. It's important to notice that our first value, our initial value, will not have a previous value for obvious reason. And then we will see something here, y2. We can compare y2. You see here the last values, 3.13, 4.35, and we compare it with the first definition I used, and it's the same. You can see. Okay, you can use both, but of course, this function lag is going to help us to write our code more simple or simpler, right? And then, okay, and in this case, because y2 first value, it could be changed, as you will see here. So it's important to initialize the back y sub 1, as you can see here. In this case, it's going to be y sub 2. Just mark it like that. Let's see, using ggplot, what we just create. As you can see here, I'm going to create some data frame called random walk, and we have the fecha, that is going to be the date, and using the x values and y for the y values, of course, is going to be our time series data, and this is our date. So random walk is going to be our time series. Here, you can see it. We have different days with different values. Simple. Then, here, I'm going to create some geom point and a geom line. That means I'm going to mark the different points, and I'm going to join them with a line. And this is our first example. And I run this, and let's talk about it. Here, we have a time series that is changing with a trend, not necessarily. As you can see, first our initial value was 2, and then it goes down because the explanation for this I find is the errors were negative, and then each time we were adding to 2, each negative value was subtracting, and then it fell. However, we have now an uptrend. As you can see, that means that different, or the most of the errors, the white noise in this case, were positive, and they were adding and adding and adding. But you can see it changed. That's the nature of a random walk. We don't know exactly how it's going to change. But then, as you can see, there is a downtrend, uptrend, downtrend. And if I rerun this, again, the composition of each element will change too. Then, one important question is the random walk stationary? As you can see, the first answer that comes to my mind is no. Because we go down, up, down, but as you can see here, this part here is shorter than the other one. That is too long compared with the other ones. So you can see the nature of this is random. That's why we can understand a random walk. Then that's our first question. Is it stationary? And then we can create another time series to understand and to compare, and maybe if it was not stationary, to make it to be stationary. We want to make it stationary. I create some vector y_diff for difference that we're going to create the first difference. What is that? A difference. Well, a difference, as you can see here, I'm going to define it as today's value minus yesterday's value. And at the end, what you're going to have, if you compare the definition of random walk, is the error. We're going to have the error. We call it E. And that's what we have here. So at the end, this difference should give us error, exactly white noise. And what is the characteristic of white noise? A constant mean, constant variance, and stationarity. That's it. There are two ways, remember, to create this. Is using the lag or using the for I just showed you for. And let's see here when we create diff. It's important to notice, remember, that when you use lag, the first position will have a null value. So in the time series y_diff, we will have our first value as null value too. Let's see. It is it. Let's see what we have here. You can see here we have different values, but they are around -2 and 2, as expected, as I was mentioning, because it's going to be errors. And then we create our second time series in our data frame that's going to be random walk different one. And I'm going to create here example 1. There you go. And let's talk about it. So you can see here, we can compare this plot with some white noise. What we can compare it with the white noise? As you can see, in this case, our errors are around horizontal line 0. Also, most of our errors are between the interval of -2 and 2. Some of them are above or below, but that's just a small number of points. You can see our variance is constant, and our errors are around 0. It's important to notice too that we have just some randomness around. Either there is not a typical trend, up or downtrend, for example. Then we convert our random walk into a stationary time series. Then let's ask exactly with a test if it's stationary or not. Let's see. We have here the library TSWGE, and we're going to use the function Ljung Box. Ljung Box is going to tell us if our time series is white noise or not. Let's see, for example, our first random walk. As you can see here, I'm calling the values from my data frame random walk, and I'm going to test it. The hypothesis is that our time series is white noise. The alternative hypothesis is that our time series is not white noise. And we're going to compare it with the p-value. And here we have the answer. You can see our p-value is telling us reject the null hypothesis. Reject h sub 0. Why? Because 0 is smaller than 0.05. And then we are not working with white noise. That's for our random walk. But let's see here for our first difference. And here you see the p-value. We have p-value greater than 0.05. We don't reject our null hypothesis. We are dealing with white noise for our first difference. Then what is the explanation for this? That we have created coming from a random walk, and we got a white noise time series. And let's see something important about stationarity for our random walk time series. We're going to use, or we can use, two different tests. The augmented Dickey-Fuller test, where the null hypothesis is that we are not working with stationary data, and the Kwiatkowski-Phillips-Schmidt test, KPSS, saying that our null hypothesis, or is established that our null hypothesis is we are working with stationary data. Let's see. Then let's run using from the library T-series the function ADF, where I remember time series is not stationary for null hypothesis, and an alternative hypothesis is our time series is stationary. And then as you can see, this is how we write it in R. First of all, we have to run time series, we call it, and this is our random walk, remember. What do we have? P-value. Okay, it's telling us something important. Our time series is not stationary. Why? Because the p-value is greater than 0.05. We don't reject the null hypothesis. Our time series is not stationary. And what about our first difference? As you can see here, I have to eliminate the first observation because it was null. And the ADF test cannot work with that in this case. And we're going to use it. Our first difference, we remove all that autocorrelation and we run it. Here it is. You can see here, p-value is less than 0.05, saying that we are working with time series that is stationary. A second way to test if we are working with stationary data is using KPSS, as I mentioned before, and the results have to be according to the Dickey-Fuller test. As you can see here by def, it means our first difference. You can see here p-value, but the null hypothesis in this case is time series is stationary. We don't reject it. And for a random walk, we have to reject null hypothesis. We are working with stationary time series data. And something important is to measure autocorrelation. It's important to notice one characteristic of random walk. By definition, one value or today's value is correlated of a previous value. Then, how to measure autocorrelation? Well, we're going to use a library card, and from here we're going to use the Durbin Watson test, where the Durbin Watson test is telling us if the value from this test is around 2, we don't have autocorrelation at all. However, if the value is way smaller than 2 or smaller than 2, we have positive autocorrelation. And if it's greater than 2, we have negative autocorrelation. Let's see for our first difference. So let's see for our first difference what we have. Do we have autocorrelation? Remember that for our first difference, we remove that dependence between today's value with the previous value. And here we have, this is around 2. So we don't have problems of autocorrelation at all. However, in our random walk time series, you see, is smaller, near 0. So this is telling us you have autocorrelation. Does this is gonna appear all the time? Not necessarily. That's a problem with random walk. The randomness of the properties of randomness of a random walk could tell us for one simulation, oh, you don't have autocorrelation at all. But if we rerun it, we could have autocorrelation. The same happens with stationarity. So it's important to explore more our data when we think or we are noticing that it could be a random walk. It's important to use too the autocorrelation plot. This is going to tell us how our data is correlated with lag values. In this case, I'll tell you, for example, here we have autocorrelation between today's value with a previous value. And then when we are moving to the right, that is mean today's value with 10, 2, 3 days back. In this case, for example, here is telling me today's values, are they lag when we lag them 2 days back? What is the autocorrelation? Well, as you can see, it's very strong. Today's value with today's value is going to be always 1 to correlate, perfect correlation. But you can see all my values are very correlate with lag values. Why? Because of the nature of the random walk. By definition, it's going to be correlated. We are going to rerun one more time our random walk simulation to understand this a little bit more. Here, I'm going to rerun again my definition. Just create, as you can see here, and I'm going to create a plot, and you will see. As you can see, it has changed. However, we still have some patterns of downtrend, uptrend, and it is completely random. We could create a difference, and we're gonna see again. We can see one more time that once we create our first difference, we eliminate that trends if still exist in our data. We can convert a random walk into some white noise behavior time series data. We can convert a random walk into time series data with behavior of a white noise. As you can see, most of our points or values are between -2 and 2 with constant value. We could try to simulate more and more examples, and we will have different responses. At the end, one of the characteristics of random walk is going to be non-stationarity, autocorrelation, and its randomness, of course. So, in the next episode, we will discuss more about time series using different libraries, different tests, and how to recreate and how to predict values with time series. See you next.